in a really cool term here. And when we've done all these series, or what? Why are we doing, what's the purpose of doing all these power series? So some of these crazy functions from before, we can actually program them, put them in the computers, calculators and stuff. Well, that's not hard. Well, think about it. How do you do like sine of x? How do you write a program for sine of x in a computer? Or e to the x, right? Those are rational numbers. And so we look trying to create power series that could represent it. You can just run it like in a computer loop that would do that. So the title of this is Representing Functions as Power Series. So what's the function? We're going to use one specific type. The function is, remember the geometric series test? Geometric series would converge to, what was that final solution? First term over 1 minus ratio, right? Well, what if we always look at everything as starting at 0? Okay? We'll look at everything as starting at 0. What would always be the first term if you stuck a ratio like this? There's your ratio. Remember how geometric series, this was always exponential? What happens when you plug in a 0 in here? What does this number always become? So I'm going to write my equation as first term over 1 minus ratio, but look what I'm putting for my first term, 1. And I want you to go, why am I writing A or first term? Because if I start this at 0 every time, what would be the first term? A 1 every time. So we'll keep that on the left. So now we're saying, what is this equal to? I'm just doing a geometric series with this. This is equal to, if you start at 0 and you go to infinity, sum radius r raised to the n. And doesn't this come out mathematically true? Yes, but do you remember when? So let's put it down. If the absolute value of the ratio was less than 1. 1. So everyone, that's the secret to section 11.9. The left side is a function. You know what the stuff on the right side of the equal sign is? This is a what? That's a power series. You notice it? I got my series. Representing functions is power series. So 11.9 is just one specific type. Hey, do you want to write this another way? If you don't like my r's, what if we made it an x? You want to write this? What would this equal? So some of you may prefer to put this in your notes. If I change r to an x, how does this play out? What's this become? Just substitute x for every r. What would you get? X to the n. And then what would this say? If. There you go. This is 11.9. You go, really? So I'm going to give you some examples. And we'll go, where is this useful? So here's my first one. And when there's a function. I mean, if you want to write, hey, f of x equals x. Sure, if you want, but that's my function. I need you to write this as a power series. And you write that as a power series. And I hope you find this easy. Are you ready? 1 over 1 minus r equals r to the n. So I'm color coding here. R and here's the r. X and this is a what? X, like that. But this is almost identical except the x or the r is now what? X cubed. So what does this become? I hope you find this easy. I'll put parentheses, I'll put the n, but what goes there now? It's not just an x. It's a x to the third. So if you want, color code, so you can see that. This was an x to the third. And all I'm doing is saying you get to go there. Just like this, look. See, I want to color code. Yellow, 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 yellow. This is now going here. And keep it that simple. Go, that's really it? Sure. Oh, I gotta say where it converges. If what? If the absolute value of what now? If absolute value of, there's my r, which is a, okay. Now, can you help me simplify this? It's not a big deal. How can I get that stupid cubed off there? Take the cube root of both sides of the inequality. So what does it become? You can simplify this. This becomes That. Because what's the cube root of 1? So you can rewrite that as that. There's, oh, radius of convergence. You follow me? Radius of convergence.
Do we always write n equals 0?
Yes. These will always start at 0 with these, with this particular function. Now, what's neat, I like your curiosity. Is it always 0? Yes, here. Tomorrow and the next day, we might get a couple, like, it might be like a natural log problem. And you go, oh, I'll start it at 1.
Okay.
But most is going to be starting at 0. All right, was that not good enough? All right, well, here's the next one then. Oh, what's another way to rewrite this? You're going to really want to do this. Not now, it's not a big deal now, but you will in our last problem today. Yes, do you notice he just multiplied these? Like you can write it without the parentheses? That's x to the 3n problem. You go, did I have to do that here? No, you found the power series. I asked you to just find the power series for that. This, everyone, what's saying mathematically? This function is equivalent to this. But it only works for what numbers? It's not very, how many, it doesn't work for many. It only goes from what? These are the only numbers for x that work for this. So if I plug in a 5 here, I can put a 5 there, it works? No. X will only converge for those numbers. Cool. But at least it does. At least it works for some. Hey, here's my next one. I'll leave this up. I'm going to leave it up so you can compare. And after this, you're basically next. What if you got this? I need help. Oh gosh. That throws it all off. Oh. I wanted this to be a what? Huh? See, this is just the geometric series, isn't it? That's all this is. That's the geometric series. But that gone, it's got a plus. Can we still play with it? How can you make this a minus? If you make this a minus, Adam, very good. So that's what he's saying. Rewrite this as rewrite it as that. One minus negative x cubed. I'll even go like this. Isn't that true, everyone? Minus times a minus is a positive, a negative times a negative is a positive. Now it's good. You ready to roll with it? What do you get? It's going to look something like this up here, but slightly different. Now what's going to the end?
Negative x cubed.
Negative x cubed. Ta-da! And when does this converge? If the absolute value of negative x cubed is less than a 1. But can you simplify that? What's the absolute value of a negative 1? 1. So I can think of that as that, which becomes that. Cool. Go ahead, Connor.
Why did you have to rewrite it like that?
I had to rewrite it like this because this is all we've got.
Oh.
And that has to be a minus.
Okay.
Someone got that? That's the focus. To get this thing to roll, in regards to power series, that has to be a subtraction sign in the middle. So we tripped it up. We go, well, then make that negative and keep that minus, and now it's working. Now I need you, it's not a really big deal here, but it is in our last problem of that. How can you rewrite that?
Negative x to the 3n.
Okay? Everyone, negative 1 to the n, multiply x to the 3n. See if you have any questions on what I just did. If you go, do I have to do that here? Not in this problem. You found the power series. Beautiful. We're about to do an integral problem. And the integral is going to be with respect to an x. Remember a dx with integrals? So I need you to get that x by itself. I don't want it jammed up with a minus in there. It won't work. You got to break it up. So this is how you break it up. Does everyone see what I did? That's a negative 1 to the n times an x to the 3n. But you do got to rewrite it like that. Hey, that's an alternating series, isn't it? That's what comes out of that. All right, so here's our first one. 2 more problems, but everyone, that's the secret to this section. Everyone okay with that? I think you got it. And you know how to deal, Connor, with if it's got a plus, we just do that, don't we? Which actually makes that emerge. If you want to kind of fast forward to what's going to happen with it. So the last 2 problems we're doing today are on our integrals. Problems, this is why I love this part. These are integrals we couldn't do before. What methods do you know for integration? What methods do you know? Integration by parts, what else? Partial fractions and U subs, right? Big integration methods. Well, we're going to use the power series. I'll put A. And I want to tell you which problem this is like. This is from 11.9. This is like number 25. To evaluate the indefinite interval. So this is fun. We finally get to put some use to this. These power series, being able to do this. Something we haven't been able to integrate before. So, and this is like number 25. Okay, here's the integral symbol. We haven't seen this in a while in chapter 11, have we? That's the first time I've written that in chapter 11. And there's a t on top. And I'm going to do 1 minus t to the 6th. dt. If you don't like the t's, you can make these x's. The book wrote t's. I know a lot of you are going to practice that, so I'll keep them t's. Again, you can write this as x's. What would this be? X, 1 minus x to the 6th, dx. I want to use a power series to evaluate that indefinite interval. Would a u sub work? No. How about integration by parts? No. How about partial fractions? Maybe, if you know how to break that up into a bunch of linear factors. Not so easy, huh? So we're going to use a power series. Katie? No. Try it. What would you do? What would you let u equal to first?
1 minus 2 to the 6.
All right, what you would have to have is, remember the power difference always has to be by 1? You need to have a t to the 5th power out there. Because what's that derivative? 6. See what happens?
Yeah.
You would need that. And that's when the u sub works, when the power difference is exponential by 1.
Okay.
Doesn't work on these, right? But you're right, if that was t to the 5th, screw this power series crap. Let's do the u sub, right? Anyone still here? Leave this symbol here. That t, that's bug me. Keep that out in front. And what's t multiplied to? I'm trying to get this to emerge. I'm getting closer. And my goal, when I'm trying to get that to emerge, I'm close. I think I've got it now. But did everyone see I moved the t? Because this didn't have a 1. What's in the top there? Always a 1. So when I had to make sure the top was a 1, so I moved that over. Now what can I put in place of that? Leave that here, just let it hang, let that t hang. What can I put here? Here we go. And when I'm going to put a power series. This cool? I am jamming this in here because I'm allowed to. It's got a something to the n power, right? This dt is still here. What goes here? I'm going to do it with color coding. Where's my yellow chalk? That's a t to the 6th. We know 1 over 1 minus blah equals summation blah to the n. We just got to put that blah there, right? That's blah goes there. So what do I put in there? This t to the 6th. Is everyone okay with this? Juliet okay with what I did? Oh, cool. Are you sure? Does everyone know why I had to leave that t out front? Because look. 1. So now, what's another way to write it? T times. Again, if you hate t's, make them x's. If you want to always do x's, because there's t's can bug students, I know that. There's nothing wrong with writing everything in x's. This would be t to the what power? Now remember, before we integrate, we're about to do the integral. Now it's not going to be hard. How do you integrate x squared? X cubed over 3, right? How do you integrate x to the 5th?
6
It's going to be that simple. It's going to be that simple. But I can't leave these broken up. I have to get this included in here. So you're allowed to move this. But if I put that next to it, does anybody know what a t to the 6th n times a t becomes as 1t? Yes. Put that in your notes if you didn't know that. I'm going to take this, move it here, and rewrite that as t to the 6th n plus 1 power. That's what I'm going to do in my next step. because I gotta be able to do this. I only want one t to some power, so I'll do that right now. You can do that, you sure can. T to the now, what power? 6n plus 1. dt. And the reason I was able to do that, t to the 6n times a t becomes t to the 6n plus 1. Now, again, what's the integral of x to the 5th? X 6 over 6. What's the integral of x squared? X cubed over 3. Yeah, plus Charlie, right? So what's the integral of a t to the 6n plus 1? You can add this by 1, then divide by it. So what the heck is 6n plus 1 add a 1?
6n plus 2.
Here comes my antiderivative. Problem solved. Here I go. What do you do with this? Just carry that. Just carry that down. T to the 6n plus 2, and then you got to divide by something. Remember? Look what you did. You pumped it up by 1, you divided by that number. You pumped it up by 1, you divided by. So what do I got to divide by?
6n plus 1.
6n plus 2, right?
Sorry.
That's all right. Hey, one more thing. I'll put the plus 1. Plus it. There it is. Isn't this cool? Everyone, this is this integral. It works. Well, hold up. For what value is a t? Does that work for every value of t? Let's go back. When will this work? I'm going to make a note. This is that radius thing. What's the radius? This only works if the absolute value of what is less than 1? And can you simplify that? So, and that's the only, I guess, negative part to the problem. This only works if the values of t are between a what? One, negative 1. You have to check the endpoints. Julia, we don't have to check the endpoints here. Make out the way so we can see that. This is only where it works though. But hey, pretty cool that you can find that antiderivative through this. So, and that's the last thing we're doing today. That was an indefinite integral. Let's do a definite integral. And does everyone remember that alternating series estimation theorem? Let's use that in the end to approximate, like how many decimal places and stuff. Cool. Hey, if they say 3 decimal places, that means how many numbers after that decimal point? 3, right? If they say 3 decimal places, we'll do that. So last problem, but this time, how about a definite? Last problem, use a power series to evaluate the definite. What do you got? This problem is like number 29. Over here. The interval goes from 0 to 0.8. Yep, 1 over 1 plus x to the 7th. Let's get accuracy to 3 decimal places. All right. The wording they use about this. Can you change evaluate to approximate? This is the wording they use in the book. So approximate, and now they're going to give you the decimal places. Well, in our problem, let's do 3 decimal places. All that means is, in the very, very last step, when we get that antiderivative, you and I are going to use that alternating series estimation theorem. Where you go, oh, the 9th term has got that accuracy, I'll add up the first 8 terms. Cool? That won't be a big deal. Not at all. All right. Connor, if you don't mind, I'm going to go to you. I'm stuck. I want to use that. But that is a daggone plus. How does it work? This has got to be a minus.
Minus negative.
That's it. So that's going to be my first step. I'm going to write it that way. I know some of you can do 2 steps at once, but I'm just gonna take it nice and slow and do exactly what he said. There you go. I'm thinking of the math problem like that. All right, now, so far so good? You ready to do it? Here it comes. Always starting at n equal to 0. What goes here? Something to the n. Last problem was t to the 6th one here. What goes here? Yes, I want to color code it so we can see it. Katie, very good. A negative x to the 7. Now you gotta help me break that up.
Negative
It's
1.
really important.
X to the 7.
Isaac, way to go. Leave this as is. And when he's writing this as negative 1 to the n, aha, we can use the alternating series estimation theorem, times x to the 7n dx. And look what letter I want to highlight. X. Get that really bright. Because dx. Because when you integrate, there's variables in here, all over the place. We're integrating only letter x, right? And how do you do an x squared? X to the 3 over 3. So that's all we got to do now, right? You all agree? Do I have to do that here? No. That doesn't have an x in it, does it? That's going to carry. That's going to carry. What's going to happen to this thing? To eliminate that integral. The antiderivative. This will become, you can say it with me, x to the 7n plus 1 all over 7n plus 1. But this, see that part? That doesn't have an x in it. That's just going to fold and carry on. Right. You got it, everyone. Bye-bye integral symbol. This is the antiderivative. Leave that as is. No x's in there. But this becomes x to the 7n plus 1. Sometimes I get this on a test. And they forget to do the what? Yeah, they don't do that. They just forget to do division of the 7n plus 1. If you want to put that series symbol bigger, you can. I'll make this thing bigger. Just so it looks better. You know, like this. It's this entire power series. Plus constant. Well, I'm not doing plus constant this time. It's a definite integral. So do you remember what you did with integrals? What did you do here? You went like this. And you put these limits of integration. One's a 0. What's the other x, right?
20.
The reason I'm writing x equal to, so you know where to substitute it. Because there's letters all over the place. That's why I'm writing those x equals. I didn't want you to get confused. Like, where am I going to put these numbers? You're substituting these into the what? Into the x. Not into the n. Not into the n. This is going where? Right there. So let's do it, everyone. You put that in there, then you put this in there, and what do you do with the 2 answers? You subtract. So let's put a point in there. What does it become? Summation n equals 0. We got this. Negative 1 to the n. And what does this x become? 0.8, right? Maybe I should make that really great. A 0.8 raised to the 7n plus 1. And what's this all over? 7n plus 1. Maybe even make this series a little bit bigger. Now when I substituted this number, but then I have to put a minus sign and substitute what number? But I'm not going to write that, because what happens when you put a 0 here?
0.
Does everyone agree? You can write minus 0 if you want, but you don't have to write that. So what is this called? This is called the integral solution. The antiderivative. This is the integral solution. But we need to get the integral approximated to how many places? So on a test, I write one blank space where I go, put your integral solution here. You would write that. And then the next place I'd go, give me the next 3 terms, give me the first 3 terms of that series. We'll fill that out, and then we'll approximate.
Do we negative plus 2?
No, because it was a definite integral. Excellent. And so this is the integral solution. Now, next thing I would say is, could you give me the first three terms of the series? What's the first three terms? And then after you give me 3 or 4 terms, hey, you know what? Since we got enough time, maybe we do the first 4 terms. Does that sound good? And I did this, I'll let you check it with your calculators. Let's do the first 4 terms. What's the first 4 terms of the series solution? All right. And if you plug a 0 in here, what do you get? What's going on at n equals 0? What's -1 to the 0?
1.
1. What's 0.8 to the 0 plus 1?
1.
0.8. And what's 7 times 0 plus 1? Alright, this is my first term. And when you get your calculators out, you can just help me out with this. What do you get for the first term? I mean, that was the first term. What do you get for the second term? That's when you substitute a 1. That's called the first term. 0.8. And when you plug in a 1, that's going to be the next term, n equals 1. I get -1 to the 1 is negative. Oh, this thing's just going to alternate, isn't it? What's this number become? What's 0.8 to the 8th over 8? I did it too, just so if you hit it on your calculators, I want to see what comes out. You can start writing this in decimal form, right? This is what I got. I got -0.02, 09, 71152. I need 3 decimal places. That's not going to cut it, is it? Let's go to the next term. It's going to alternate. Now do n equals 2. What's going on n equals 2? So if I put in a 2, negative becomes a positive. This number right here, 0.8 to the, that'll be 15 over 15. You just hit it on the calculator, right? Unless you want to use, if you like to use the L1 thing like I did before, that's fine. But you're really saying it's positive 0.8 to the 15 over 15. This is what I got, just to save some time. I got 0.002. 3, 4, 5. 625. Okay. That's not going to cut it, is it? Look at that. Because I'm trying to see, eventually I'm going to get like a 0, 0, 0. So what's n equals 3? This will be the 4th term, right? This is the 4th term right now. And it's going to change back to a negative. And I got, negative point triple 0. Ooh, all right. 335. 395. And I want to put a big box on it. I want to hear the first 4 terms of the series. I'll put pluses next to them. Positive, negative, right? It's alternating. And I will have one more space for you to fill in during the test. The idea, approximate the def integral to 3 decimal places. So the solution approximated to how many places? To 3 decimal places. Okay. And if you're curious, if you wanted to double check this, you might even look at putting in the 5th term. When I add up these 4 terms, the number I got for the sum is 0.7810. I want to say that again. I add this, and this, I get 0.7810. If you add the first 3 terms, I get 0.7813. Do you notice the 0.781 did not change? Anyone got that? So guess what my solution is?
171.
0.781. And this is by the alternating series estimation theorem. Because this had that what? That desired accuracy. Someone see this right here? It didn't guarantee it, but I was like, boy, I threw 3 zeros. I think by the alternating series estimation theorem, I only have to add these. And I checked it out. Sure enough, that was true. Just adding this 4th term didn't change this number right here. Cool? Now, I have a big suggestion during an exam. Try not to forget this. I approximated this to how many places? 2 decimal places. And I only had to add which terms? I really only had to add these first 3 terms because this just made it more accurate, but by the alternating series estimation theorem. And in the fourth term, because this had that desired accuracy, only had that these first three. But put this in your notes. If you're on a test, how can you make sure you don't miss this? What do you have on your desk? Probably. And where's the John? You'll borrow mine. But no, bring his, right? What we have with you? A calculator. What does your calculator do? Can't they approximate what? By Math 9? So I would take the time, would you right now, and check it? Would you do Math 9 of this? Go from 0 to 0.8 and check that the first three what? That you did it right? I would definitely do that because you have the technology at hand. Just to make sure, right? Does this really make sense what we're doing? And as you're doing it, does anybody know, I made up this problem. Does anyone know why I didn't use like 1.5 here or 2.3? I remember the radius of what? The radius convergence, this dude it only converges for x values between a 1 and a negative 1. That's why. So I gotta do something similar on a test. Did it work? Now you're gonna get it approximated, but here's the story here, why I love this section. How did that do that? What was the magic involved? How did that computer do that? It likely ran into a what? Ran into a power series. You follow me? How did this, can I pick it up? How did this machine come up with that answer? Some computer scientist wrote a program that modeled a power series, right? And ran through a power series. Isn't that cool? So now you're learning how these are designed. Who are the computer science majors? Oh, cool. You probably eat this stuff up. That's me. Hey, great job with this. Have a great day.